start by the time introduce
Kiran, shall we wait for some more time? Let some more students join. Yeah. Hello,
Yes.
Kiran. Yes, Kiran.
Yes, fine. Okay.
Yeah. So, Kiran, we can start. Hello.
Yes, we can start. Can you hear me?
Yeah. We can hear you.
So, shall I start introducing?
Yeah. Only one sentence I would say, and then you can proceed with that.
Yes.
Good morning, everyone. On behalf of Hindi Vidya Prachar Samiti, Ram Niranjan Jhunjhunwala College, I, Dr. Neeta Srivastava from Physics Department, welcome one and all, especially our today's speaker, Dr. Sai Vinjanam Pathi. I would like to thank our principal and our director, all my vice principals, to have given us this opportunity to present such types of talks. We are really obliged to them. I would like to hand over my mic to Dr. Kiran Polwankar, who is going to give introduction about today's speaker. Thank you. Yes, Kiran.
Yes, thank you, madam. It is my pleasure to introduce Dr. Sai Vinjanam Pathi. He did his BSc from Jain College in Chennai. Then he did MSc in IIT Madras, and then went to Indiana State University for his PhD. There he had postdoctoral stints at Boston and Singapore. Then came back and joined IIT Bombay. He has vast experience of working in quantum system and nonlinear dynamics on the interface. So basically complex quantum systems. So we are eager to hear him. Let's go straight away to him. Please, Dr. Sai, please start your presentation.
Thank you very much. Thank you for having me. Can you hear me?
Yes.
Okay, fantastic. So let me just begin briefly by sharing the screen. And you can see the screen just fine, right? And let me move this out of the way here. Can you see this screen? This is the title slide. You can see the transition.
Yeah, yes.
Okay. So thank you very much. Thank you for having me. It's a great pleasure. We're neighbors, we're fellow Mumbaikars, so I'm very happy to be here. And so this is a talk that I've tried to put together to try and be accessible to first year, second year, third year undergraduates, and also hopefully that the master's students will take something away from it. So I just want to talk to you about quantum mechanics. This is one of the main areas of research for me, but I also want to talk to you about basically basic quantum mechanics, nothing complicated, nothing out of the ordinary. I just want to give you a different perspective, a perspective that's quite common and well known within the research communities, but I think there needs to be a little bit more work done for us to share it across the community. So I'm happy to talk about this with you today. So I just have two brief warnings / requests. So the first of this is that in a previous talk that I gave, I was told that the students have sometimes have difficulty with technical English words. So just as an aid, just as a help, I've translated some of these words. I'm not proficient that much in Hindi. I can speak it just fine. So feel free to basically stop me and ask me questions. And this is the second part of the thing. Feel free to stop and ask me questions at any time on the talk, and feel free to stop and ask me questions basically in any almost any language that you're comfortable with. I speak Hindi. I also speak Tamil and Telugu, if that helps. Okay, so with that, let me just begin by basically making zooming out and taking a broader picture. So, what do we learn in school? So again, I apologize. I've set this up in such a way that first year undergraduates can still follow through the entire talk. So, so I've set it from that perspective. So what do I learn in school when I leave high school? I learned something about motion, something about Newton's laws, maybe a little bit of thermal conductivity and things about thermal properties, heating and cooling, a little bit about waves and oscillations. I maybe look at the differential equations involved, and a little bit of refraction, reflection theory, electromagnetic theory, electricity and optics at some in various capacities. Of course, your mileage may vary depending on whether you went to this state board or that central board. Okay, but what's waiting for you? Like what actually is happening in research departments out there? It's this exact same stuff, but at the frontier, it's far more exciting, and I think this excitement is what many folks are drawn to and are interested in. So I just share with you a little bit of that excitement today. So of course, there are buzzwords and phrases like black holes and time travel, which people come across. There are legitimate physics reasons to discuss these things. Of course, black holes are perfectly legitimate. Time travel has been kind of, has also been in the science fiction, has been discussed quite thoroughly in the science fiction universe. So if you're going to discuss it within the realm of science, we have to be very careful not to violate causality and so on and so forth. You could ask questions like, what are the consequences of the finiteness of the speed of light? Or the speed of propagation, or the speed of causality, however you understand this phrase. What are the consequences of the uncertainty principle? What are the consequences of canonical commutation relations? How do I understand the stability of matter? Mostly atoms are made of nothing. And so one of the big questions in the early 20th century was, why doesn't stuff fall through each other, basically? Because if atoms are made of nothing, then how is it that if I put a cup of coffee on a table, it just stands there? So on and so forth. How do I understand the melting of ice, right? So till now, basically the list of questions that I'm asking or saying out loud are questions that you perhaps have thought about before. Perhaps you've even come across them in your textbooks, in your standard textbooks. Certainly I had come across them during my undergraduate years. There are some other questions which are a little bit unusual to ask, but there are still questions that pertain to physics, and that physicists, I think, should ask these questions, because we gain a lot by thinking about these. And that last question in my list is one example of that, which is, what are the physical limits of computation? So if you think of a computer as basically a piece of hardware that basically transforms inputs to outputs, that you feed it a program and it gives you a result. If you think of it as a piece of hardware, then you'll conclude that the laws of physics apply to it. Whereas if you think of it as something that processes software, then the software has a different set of rules attached to it. It has the rules of computer science attached to it. So how do you reconcile these two? And this is one of the modern areas of science that I work in. Okay. So how is this all organized when, in your undergraduate curriculum right now, how is all of this organized? It's organized typically in the pillars, in terms of the pillars of physics, so that these pillars, if you have sufficient control over, then you can proceed to kind of think about the more complicated stuff. And so you learn classical mechanics, you learn electromagnetic theory, you learn thermal and statistical mechanics, and you learn mathematical methods, which is, of course, the kind of foundational pillar required to even discuss the other pillars. And then you learn quantum mechanics. And often, basically, what is not sufficiently clarified is two things. One is that the reason that you're learning this is so that you can learn to put them together carefully. And so, most things are a complex mixture of all of these things. So if you want to discuss what happens to transistors as you're cooling them, or as you're making them smaller and smaller and approach basically nanometer scale, then you have to kind of bring many, many ideas from many places together and make them talk to each other. The second is basically so that you then get to go back and question basically the differences in these various pillars. So any fundamental theory, right? So if you're very interested in theoretical physics, one of the kind of high-minded statements that somebody can make is any fundamental theory can be thought of as basically belonging in two camps, and we haven't fully reconciled these two camps yet, but belonging in two camps. One camp basically is about the uncertainty principle being right, and the other camp is basically about speed of light being constant and its consequences basically. And so I just want to concern myself with the fact that this camp, which is the uncertainty principle being right, is actually very mathematically straightforward to discuss. It's actually the algebra of it, the maths of it is just algebra. So it's completely straightforward, but the physics of it is somewhat subtle, and I just want to share that with you. Okay, so let me be more concrete. What I want to say is the following, which is that there is, in all of these different theories, there is one theory that stands out, quantum mechanics, which stands out, and it stands apart from especially Newtonian thinking. And it's, as far as Newtonian thinking applies to thermodynamics and applies to waves and oscillations and standard electricity, it also stands, it pushes all of those into that category. Quantum mechanics has subtle implications, which basically challenge the way we think about classical mechanics and the way we think about the world. And this is basically the rest of the story I want to tell you. Now, what do I mean by this? What do I mean by the fact that classical thinking is different from quantum thinking? What I mean by it is that there are some inherent assumptions that are built into the fabric of quantum mechanics, that are built into the fabric of the way we think about the world, that are indeed challenged by quantum mechanics. And quantum mechanics challenges them and then points out to you that some of these inherent assumptions are wrong and or are incompatible with experiments. And so this is the story that I just want to share with you today. And not only is this interesting from the point of view of physics, it's very interesting if you do nothing else with it but simply contemplate it, meditate on this. But it's also interesting, deeply interesting from an application point of view. So if you're interested in the real world and the material world and engaging in the world that is full of technology, then as well you should be interested in this, because this philosophical differences usually usually are simply left as something that you discuss over dinner time, but these philosophical differences actually have technology implications. And so that's what I want to share with you today. Okay. So what are these inherent assumptions, right? What are these things that we're thinking of in our heads that we never say out loud, right? The inherent assumptions I want to just highlight, I'll handle some of these, but not all of them, are reality, right? So by that, what I will mean in this talk is physical descriptions are actually happening, right? I will discuss each of these things. Locality simply means that something that's happening over here has nothing to do with something that's happening in Delhi, right? So things that happen over here happen over here. And if I want to make something in Delhi happen, it can only happen at the speed of light. I have to actually communicate with Delhi. I have to pick up a phone, call someone in Delhi, and then ask them to do something. And that can only happen at the speed of light or slower. Determinism, right, which is something that's an inherent assumption in the way that we think about the classical world. If I throw a rock, all you need to give me is the initial conditions. The laws of mechanics completely determine what's going to happen. There's nothing else. There's no other choice left in this discussion. And so, you know, one way to kind of make that point, I want to make that point, is by saying there is no such thing as inherent randomness. There is no such thing as me throwing a ball and the ball deciding randomly to do something in the middle, right? And the last is the most highest philosophical ideal here, which is the question of free will. Can I make free choices, right? All of these will start getting entangled into basically our discussion for the rest of today's talk. And so this is what I want to present to you. So let me take on basically the first question, the question of reality, right? So let me, again, I'm using heavy metaphors, and they only can carry so much of the scientific discussion. So if you feel displeased or dissatisfied with any of the metaphors, ask me to clarify, and I'll just say the physics thing to you, and then we can perhaps find clarity in that. So the metaphor that I want to bring in front of you, if you've never had this discussion ever, is with reality is the following, which is I think it's I learned it as a Buddhist adage, but you know, wherever it came from, the statement is that the question is the following, which is, if there's a tree that falls in the forest and you're not there to hear it, did it make a sound, right? So do trees make sounds and then we just happen to hear them, right? Which means that we're passive observers of the sound. Or is our presence the thing that causes trees to make sounds? This is a question, right? Of course, we all believe that trees, when they fall, make sounds. And the reason why they make a sound is because they're hitting other objects. And when two objects strike each other, there are vibrations. And the vibrations cause undulations in the constant pressure of the air, even if I make that approximation. And hence that pressure is basically transmitted through the air, which I hear as sound. And so I believe, you know, if you asked me this question when I was in 9th grade or 10th grade or something, I said, I would have answered in the affirmative. I would have said, as much as I understand about science right now, I will make the claim that a tree falling in the forest does make a sound, whether or not I'm there to listen to it. And that's classical thinking already. So the classical thinking, to translate it or to kind of underline it, is basically that if I take a ball and I toss it in a trajectory, so I make a projectile travel along a trajectory with some parameters of the problem that I've defined here, so that it's some high school problem we can solve, then the role of the observer is passive. All that the observer does is simply notices what is happening, but he or she, the observer, has no role to play in the dynamics. The dynamics happens no matter what you're doing, right? So this is the exact same thing as saying, the tree that is falling in the woods is going to make a noise, and all that you have the capacity to do is basically either listen to that noise, be there to witness this event happening, or not be there, and the event happens without you. So the observer is entirely passive. All that the observer does is either records the event or does it. Cannot affect the event. So is this true? Is this actually true in physics? How did we even get to this kind of a question? The reason why we got to this kind of a question was because of the question of the Young's double slit experiment. So the Young's double slit experiment, I'm sure all of you know this, but maybe there are first years who have not yet gone through a formal discussion on this in the class. So I apologize to the experts. The Young's double slit experiment is the following experiment. So you take some sort of particles. In this cartoon, these are electrons, but just as easily they could be, you could take a trough of water, and they could just be basically a particular source of vibration. So it could just be a stick that I dip into the water to generate oscillations. So it is some pattern, it is some particle or wave, and that particle versus wave is the discussion that is quantum mechanics, but let me present it in a slightly different way. It's some particle, in this case electrons, that basically are sent from a source, and they have to traverse basically two slits, a double slit as it's called, and then they have to make their way to the screen, and they're recorded on the screen basically because these electrons, when they strike the screen, basically they do some chemistry which you can detect. So now the question is basically, what are these electrons? Right? How do I think about electrons? Right? Remember what we just discussed a second ago. We discussed that that electrons are nothing more than basically projectiles when they travel along trajectories. Are real. They actually travel along trajectories, and all that you may or may not do is observe the trajectory which is happening. So if I think of electrons as tiny balls, which is what I would think of if I was in high school, if I think of electrons as tiny balls, I would make the exact same discussion. I would say this electron is a tiny ball. So all that this tiny ball can do is it can travel through one slit, or it can travel through the other slit, and then make its way to the screen. So now the question is, how does the interference pattern happen? Because remember that interference pattern happens only between waves, right? When you study in high school or in college, when you study interference is a wave phenomenon. So how does one reconcile this? How does one reconcile this? So the usual way in which one reconciles this is basically by making the argument that there are many electrons that are running around, right? So this is what this cartoon basically shows. If I think of these as trajectories, right, then what I will conclude is basically that each electron which is coming will come and it will strike the screen somewhere. It will either strike the screen on the left or it will strike the screen on the right. In this cartoon, what I'm showing is that the electrons are traveling perpendicular to the screen. If I also allow for some variation in the angles, then you can generate a tiny spread here and a tiny spread here. But the spread, as it is, as the technical term for it is bimodal. So there is one little spread over here and one little spread over here, and there's nothing in the middle. Crucially, there is no interference, right? So how do I reconcile the fact that there was interference in the Young's double slit experiment, as seen by many experiments? The typical reconciliation for this is, oh, I saw these trajectories, I saw the trajectory, and if I think of electrons as point particles, basically then all I can say is that I can see the trajectory going from here to the screen, and I can see this ball going from here to the screen. And so maybe there were multiple balls here, and so there are multiple answers you can give as to why you see the Young's double slit experiment. Answer number one you can give is, you can say there are multiple balls, right? And this is what we will disprove in a second now. And answer number two that you can give is, if there are no multiple balls in the experiment, then the answer number two that you have to give is, my thinking about electrons traveling through trajectories even when I'm not looking is wrong, right? So these are the two choices that I have. So I went through that a little bit quickly. So let me pause and restate my claim. What I claim is the following. Electrons start from the electron beam gun on the extreme left of the diagram in front of you. They traverse the Young's double slit, and then they make it to the back end where they show interference. Experimentally, we see interference. Statement number one. Statement number two, I want to explain this interference. So the way I explain this interference is basically, first I attempt it classically, and I attempt classically by saying that maybe these electrons are particles, and the particles are simply making their way through one slit or the other slit. This argument fails immediately, because how can particles interfere? They don't interfere. Rubber bullets don't interfere if you pass them through two doors, right? So you can't explain the interference pattern that way. So you need a different explanation. The different explanation that usually people attempt is that multiple electrons are there, and so one electron over here is interfering with another electron over here. I don't know what that sentence means, but that's what's happening, right? So this was the question basically in front of physicists for a very long time. And so what I want to show you is actual experimental evidence. So this is a very famous video from Hitachi by Tanamura. If you search on YouTube, you will find this exact same video. I'm also happy to provide a source. I think there was a source here. It's just hidden by just the way that this PowerPoint export is working. So let me just walk you through this discussion. So what the gentleman who's describing the experiment is saying is, now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. So what you're looking at is you're looking at the screen, right, at this right-hand screen of a Young's double slit experiment where electrons are going to go through. And what he's first telling you is that the bright spots that appear in front of the screen in front of you, those bright spots indicate individual electrons hitting the screen, right? So, okay, so far so good. All that this shows is that the gun is working. Sorry, I shouldn't have restarted this. Right, so we're back to the same place. These spots indicate individual electrons. Electrons are only sent out occasionally, and this defeats the second argument. So remember, my argument was that maybe multiple electrons are present and somehow they're interfering with each other. I don't know what that sentence means. And so this argument is defeated by actually making this part of the experiment, by making the experiment in this way. So electrons are only sent occasionally, right? So remember that if I take a hot gas, right, I can calculate the speed at which the gas travels, particles of the gas travel, right? It's a application. It's a application of kinetic theory of gases. And so by looking at the speed of the gases, basically, I can calculate how long it will take to traverse a trajectory, a 1 centimeter line, basically, a distance of 1 centimeter. So I can tell you basically if I heat silver atoms to a certain temperature, I can tell you how fast these electrons will go and hit the thing. So what in this experiment, what they're doing is they're basically sending electrons. The electron sources are so dilute, basically, that electrons are only sent occasionally, and therefore the chance of finding one electron in this microscope, it's actually a microscope, the entire device, in this microscope is very small, right? So just read this as Young's double slit experiment, is very small, not to mention the chance of finding two, right? So the chance of finding two electrons is negligible. It almost never happens, right? So let's continue. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed at random through either side of the biprism. The biprism is the double slit. Either side of the double slit, thus creating a uniform distribution, right? So this distribution, the two band distribution that we're talking about, right? Without any interference accumulating, right? The crucial point here is that you expect no interference to accumulate because there's only ever one electron in the Young's double slit experiment. Now, let me just speed this up. What you see is that this experiment is running very slowly. So this is 30 minutes of the experiment rolled into basically less than 1 minute. And you can clearly see the interference patterns in the middle, right? So you can clearly see the interference pattern in the middle. And this basically brings us right to the point, which is, now, what are the two assumptions that I had in my head? Assumption number one was, I said, I have to insist on trajectories. Electrons have to be thought of as balls. And because electrons have to be thought of as balls, I concluded that electrons can't interfere with each other, with themselves, because balls don't do that. And hence, I need multiple electrons to even attempt a solution, right? Then multiple electrons maybe make like an ocean, and then you can have waves in the ocean or something like that. I have some assumption in my head that I need to think through, but it is based on classical thinking. By only sending one electron at a time, I have removed all of these assumptions out of the equation. And the experimental facts that remain are still that you see interference, which means the only conclusion you can draw from it is that my assumption of trajectories is wrong, right? So this is basically one of the many experiments that you could start the discussion on quantum mechanics from. Now, from here, what you have learned basically is to then start off with standard quantum mechanics. But before we do that, let me just tell you the real conclusion, philosophical conclusion that many people arrive at, which I also want to share with you, is the following, right? The Young's double slit, the single electron Young's double slit experiment leads us to the following conclusion, which is counterfactual questions are disallowed, right? Let me say what that means. So the cartoon in front of you is of a boy who is going to the bus stand near his house to take the bus every day to school, right? A sight that we're quite familiar with. Now, this is Bombay, which means that we have a robust monsoon season. And so the boy needs to carry an umbrella with him when he travels to school during the monsoon season. Now, one day, he forgets his umbrella. And so he goes home, takes his umbrella, and comes back to the bus stop, right? Waiting for the bus. And as he's coming back, he notices that he's just missed the bus. That's the cartoon in front of you, right? He's just missed his bus. So what does the boy say later on to his friends or to his school teacher? He says, if I had not forgotten the umbrella, I would not have missed the bus. Right? Does everyone agree with me? This is an example of what is called a counterfactual statement, a statement about something that has not happened. And you're not allowed to make these statements in quantum mechanics, right? Because in quantum mechanics, the statement that you're trying to make essentially is that if I had seen the electron, it would have taken this trajectory, right? That's the real statement that you try and make. And any experimental verification of that by actually trying to look at the electron trajectory destroys interference. So there is some profound, not just mathematical consequences, but also philosophical consequences that happen in quantum mechanics. And here is the first one that I present to you for your amusement, if nothing else, which is that you're in our daily lives, we make counterfactual statements all the time. You know, aise nahi hota to waise hota. You're just not allowed to make any of these statements in quantum mechanics. All of those statements are just wrong, basically, have no merit, basically. And because if you make those statements, you're violating the fundamental principles of quantum mechanics. So this, with a little bit of more work, will lead you to basically the wave function description, the standard Schrodinger equation, and then down this this well of techniques that we usually introduce you to in the undergraduate years, which is basically how to solve the problems of quantum mechanics, given that we have wave functions and the Hamiltonian, right? So what we have done is we have replaced basically position and momentum, which are observables in phase space in classical mechanics, with something called a wave function that exists for a single electron, is a delocalized object which exists in all space and at all time. And that object is the one that basically ends up being the description of reality. It's the state. It's the state of description of the system, and that profound change usually is presented as a technique change, an axiomatic change. But I also hopefully have shared with you what its philosophical implications are, right? Okay, so so that was about reality. So let me talk a little bit about the other three in a combined fashion, because I'm about half an hour in and I want to make sure to end on time. And to do this, what I want to do is I want to try and share with you quantum mechanics as a game, right? So what I'm going to do is basically just play a game with you. And so I want some audience participation. At some point, I'm going to ask questions and hopefully you'll give me answers. So the game is basically, it's a game of magic cards. So the magic cards game is basically very simple, which is you draw a card and then I draw a card, right? So that's it. The only rule, one of the only two rules of the game. You draw a card, then I draw a card, right? So we'll play the game. The other part of the rules are basically that there are only 4 cards available, 2 of which are black, 2 of which are red. The blacks are 7s and the reds are 2s. And the blacks come in 2 different shapes, which is clubs and spades, whereas the 2s come in diamonds and hearts, right? So the other rule of the game, so you draw a card and I draw a card after you. The other rule of the game is basically that these are magic cards. So both of us cannot draw cards of the same color. That's it. So you draw a card, I draw a card. If you draw a red, I can't draw red. If you draw black, I can't draw black. That's it. Those are the only rules of the game. So, right? So let's play. So you drew a card and you drew 7 club, right? I don't know how to say it properly, but 7 of clubs of 7. I drew this, you drew this card. What cards am I allowed to draw?
2 of diamonds or either 2 of hearts.
Very good. So the crucial observation here is that you're not allowed to draw the 7 of spades, right? That's the one card I am not allowed to draw, right? But which one of these 2 do I draw?
That's 50-50, no?
Either is fine, right?
Yes.
Yeah, we don't know that it's 50-50 because they're not, I've not told you that they are equal probability, but
Okay.
You have to ascertain that. Very good. You have to ascertain that. But let's say that I draw, this time I draw a 2 of hearts, right? So let's play the game again. You draw 2 of hearts. What do I draw?
Either of the black cards, like 7 of clubs or spades.
Same game. So exactly. So all you know is that the 2 of diamonds is prevented. I am not allowed from drawing the 2 of diamonds, but I can draw any of the other 2, right? So maybe this time around I drew the 7 clubs, right? So this is basically, what is this teaching us? This is a model of quantum mechanics that I just put in front of you. What is this teaching us? What it's teaching us is 2 things. One is that measurement outcomes for me can restrict measurement outcomes for you, or the other way around, right? One measurement outcome can restrict the choices available to the other person, right? This is something that that is a crucial ingredient of quantum mechanics that we will going forward, we will basically use all the time. The second is that just because something is restricted doesn't mean it is completely determined. In fact, there is still a lot of choice available to me, right? So in the example that I just showed you, just because you drew a red doesn't mean that you know which black I can draw. All you can tell me is you're only allowed blacks now, right? Which black card I'm allowed to draw is still up to me, basically, or up to choice. So this is basically the 2 pieces, the 2 lessons that I just want you to carry forward with you, right? But you should basically ask me, why is this not classical mechanics, right? After all, the whole story that I'm trying to tell you today is that quantum mechanics and classical mechanics are not like each other. Quantum mechanics is a superset, is a super theory of that has classical mechanics inside it. And in general, quantum mechanics is more complicated. And the philosophical way in which it is complicated, one of the many ways in which it is philosophically complicated, is that these counterfactual questions are not allowed, right? So, and then I'm going to talk a little bit about the other 3, which is these measurements, what the consequences of measurements are. So you can say, look, I don't know what quantum mechanics you're trying to sell to me, but this is just a card game. And I don't believe you. I don't believe that this is somehow strange or different from classical mechanics. Now, how do you prove that it is not, I'm playing devil's advocate for myself. How do you prove that this is not something strange? You make an observation. And the observation that you make is, you can say, what is surprising about this? Suppose there is a wizard in the middle, right? And so the cards that are given to you and me are not given, basically, we don't have completely free choice. There is somebody in the middle who's controlling the free choice, right? And this wizard, what he does is he basically takes all 4 cards and he sends it to you, right? You pick something. So let's say you pick the 7 clubs and you send it back to the wizard. Then the wizard simply sends me the 2 reds and he says, hey, pick one. Then I pick basically 2 of hearts or whatever, right? Then what happens is basically that your choice, if it is black, my choice is always red. If your choice is red, my choice is always black. This constraint that I have placed different colors for different people, This is preserved, but there is nothing weird about it. There's no quantum mechanics necessary. All you need is one more person that is hiding and is making these decisions for you. And in fact, he makes all the decisions. He decides whether basically to send all 4 cards to the girl, or to send just 2 of the cards. Maybe he only sends her the black cards, and she picks one, and then he sends the red cards to me, and I pick one, and he can do it simultaneously. This is another way to play the game. In which case, no matter what choices we pick, we always look like we're playing magic cards. But we're not playing magic cards, we're just playing his game, which is not magic cards, right? We're not playing quantum mechanical games, we're playing classical mechanical games. So the presence of a wizard in the middle already defeats me, and any argument that I could make about quantum mechanics, right? So this argument in the middle is basically, it's a very strong argument. It has lots of philosophical implications. It has been discussed a lot. It's basically what's called the Bertelsmann-Sachs argument. I just want you to note the role of the observer here, right? So the role basically that this person plays is that he already prearranges. He has the capacity to prearrange for you who gets black and who gets red. He makes the choices, and he can make them appear random. So always, sometimes I get black, sometimes I get red, and in those I have some choice available, but nothing is strange. This is all orchestrated by one more person, right? There's nothing quantum mechanical about this. So that's the beauty of basically this argument, which is it defeats the first order argument that I'm presenting, that somehow quantum mechanics is only about making restrictions in choices, black versus red, and about giving me choices in the measurements, which is hearts versus diamonds, right? If this is all that quantum mechanics was, you only needed one more person and you could defeat it. This is not what quantum mechanics is, so there is more to it, and this is what I want to show you. So you can avoid this by asking so the first way to try and avoid this, you can ask the magician, the wizard, to send basically his cards to both you and to me at the same time. So we share fairly reliable cell phone clocks now. So we can say at exactly 12 noon, please send us both cards, right? So, but this can also be defeated by him by simply sending both blacks to one party and both reds to the other party, or both reds to one party and both blacks to another party. So inherent randomness and basically choice within it and restriction, all of which can be covered by quantum mechanics, right? So so you can play multiple rounds like this, and you wouldn't be able to decide whether or not there is a third person involved in the story, right? So how do you defeat this, right? How do you decide whether or not the experimental observations that we're looking at, which I will show you in a second, the experimental observation that we're looking at is actually just the classical mechanics of 2 parties, right? Alice and Bob is typically the phrase that's used in quantum, of 2 parties with one hidden variable, right? One wizard who's hiding behind the screen making decisions. Or if it is basically genuinely quantum mechanics, if it is, right? This was the question that Einstein had, many people had, and so one modern cousin of that question is what I'm presenting in front of you now. So the way you avoid this, you prove that there are no wizards in the universe, that quantum mechanics is a purely is different theory from classical mechanics, is actually by making multiple choices available, right? So in the example before, basically what I had done was I had asked you to choose either red cards or black cards. Those are 2 choices that I'm asking you to make. Instead, let me ask for multiple choices. So let me change the game a little bit. So now I changed the magic cards game. And the magic cards game can ask basically, there are red cards and there are black cards. And the red cards previously appeared as birds of 2 different varieties, right? A chicken or an owl. And the black cards appeared in 2 different varieties. They were ants and ladybugs, right? So this was the kind of, this was the choice that we were basically making before, right? So this was one kind of 7, this was spades, and this was, right? So there is one more choice which is available, and that choice is basically not available in classical mechanics, but is available in quantum mechanics. And so before I show you the choice, I want to show you the choice as in a cartoon fashion. And that choice is your choice of asking the question, right? So it makes no sense to say this in classical mechanics, but I say it anyway, which is you can choose if you could choose in classical mechanics whether you wanted to see birds or you wanted to see insects. So suppose you wanted to see birds. So both of you wanted to see birds. Then when you open your box, you would see one of the birds. You would see either a chicken or you would see an owl, right? If you both insisted on insects, you would see an insect or an ant, and you would see a ladybug, right? But if you ask different questions, right? When the wizard wants to send you a bird, you ask about insects, then the wizard doesn't know that. Then basically he sent you the wrong stuff. And so when you open the box, you expect to see insects, but you see birds. Then immediately you know somebody's interfering, right? That's the kind of setup that you want to have, so that you can detect that somebody's interfering, right? This kind of multiplicity of choices, and also you can choose to ask different questions. Why should both of you ask the same question? So maybe you want to ask about insects and I want to ask about birds. Then what does the wizard do? What's the choice available for him? He doesn't know whether you will choose insect, I will choose insect, you will choose bird, I will choose bird, we will choose different. There are 4 choices available and he can't decide, right? This is a game that he can't play. So no wizard in the middle can actually play this game, this complicated game, right? So this is exactly what quantum mechanics gives you. This is the bottom line.
Sir,
yes.
Just one thing. Are we changing our choices in between the observations? Like when we have told the wizard to give us something?
Exactly. You're changing your choices in between observations. Exactly. Right.
All right.
And I'll actually make that point. So I've made this cartoon of an atom in the middle here without saying anything about it. And the reason for it is actually these are atomic sources which are spitting out identical boxes. And the identical boxes basically have either, and then I can choose whether I want to ask questions about insects or birds, and the other side can as well. And then this multiplicity of choices, there is no preparation of the boxes, classical preparation of boxes beforehand, which will satisfy all the possible measurement outcomes that we can get. This is the whole story. Yeah. So all I'm going to show you is switch to quantum mechanics and show you that for the rest of the time. Yeah. Okay, so what is all this? So you might be getting fairly tired of me switching between analogies. So let me just describe the maths to you now. So the maths is basically very simple, which is that what I've been referring to is card choices or animal choices, birds versus owls, are basically 2 different states of the spin orientation. So spin up and spin down. And what I've been referring to you as basically insect choices are 2 different superpositions of quantum states, up plus down divided by square root of 2 and up minus down divided by square root of 2, right? For those of you who are in the first year, let me just very quickly point out to you what all of this means. So if I take silver atoms, this is what's called it's a very famous experiment called the Stern-Gerlach experiment. If I take silver atoms basically are heated in an oven, and then they're emitted through a narrow slit, and a collimated beam of silver atoms is projected onto an anisotropic magnetic field. And the reason that you need the anisotropic magnetic field is because the gradient of mu dot d is the thing that carries force. So you need, if you want to pull spins apart, you need basically an anisotropic magnetic field. And this anisotropic magnetic field, what it does is it separates the 2 spins and it sends the down spins in one direction and the up spins in the other direction. And in fact, up and down are simply random labels. They're just what we've decided because this thing is pointing along the z direction. It's pointing along our up as we humans like to think about it. And so we've just labeled this as up and we've labeled this as down as 2 different choices. And these 2 choices, along with the linear theory in quantum mechanics, basically carries you the rest of the way. Now, what if I want to measure basically, so when I say that I'm going to make a choice to look at insects, right? This was my look at birds. This was my absurd statement 2-3 slides ago. That absurd statement now I want you to replace with a more technically correct statement, which is I am choosing a measurement basis, right? I am choosing to take my Stern-Gerlach setup and I'm choosing to point those magnets along the up direction in my room, in my experiment, right? What about plus minus? What about this basis? This is simply actually a rotated Stern-Gerlach experiment. It's a Stern-Gerlach measurement, the exact same thing, but instead of pointing it along the x direction, I point along the z direction. I point it along the x direction, right? I simply take this and rotate it. And if I rotate, if I leave it along the up-down direction, then I get up-down choices. If I rotate it, then I get these plus minus choices basically. And this plus minus choices basically, how to perform the rotation. You don't physically rotate it, you have to do something. It's okay, we can just ignore this for the moment. These two choices and these two choices are basically two of the many, infinitely many basis choices that I can make. So for those of you who are mathematically prepared, all I'm doing is actually I'm just choosing a basis for two-dimensional vectors, right? Two-dimensional vectors. A good basis of them is 0, 1, and 1, 0. I made a typo which I didn't realize. This should be 0, 1, and this should be 1, 0. It should actually be 1 here and 0 here. 0, 1, and 1, 0. And then basically these plus minus is basically just given by these two, right? And so these are two of an infinitely many choices of bases that are available. And this infinite variety of questions that you can ask is the thing that a wizard can't keep up with, right? Okay. So what is the take home? The take home is basically the following, which is that quantum mechanics does not allow for predetermined choices. And so determinism as a whole that we think of in classical mechanics, in the classical world, which is if I throw a rock, it just lands somewhere and it just stays there. This is basically not even allowed in quantum mechanics. Measurement outcomes are inherently random, right? This is another way to say this. And this is a big philosophical point. There is actually a strong philosophical statement attached to this, which I won't dwell on any further. I have roughly maybe 10 minutes more. And so let me just very quickly tell you an application of this. And the application of this is basically in sharing secrets, right? So the cartoon that I want to show you is the following. So I have two cats. My elder cat, let's say he wants to tell me that he's hungry, right? And so what he can do is, he's a very clever cat. So what he can do is he can take the word hungry and he can make what is called a substitution cipher. So you can go to the letter H. H is the number 08. So those are the first two letters, 08. U, he can look up. U is the number 21. That's the next two, and so on and so forth. So the word hungry in decimal, in just digital notation, this translates into basically number notation, this translates into this. And then he can convert this to binary. And here is a long string, right? And this binary he wants to convey to me, right? Why would you want to do this way? This is actually the way in which standard communication, when you write an email saying, dear sir, I would like to blah, 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 this is what's happening. Actually, it's just that English is just converted into binary, and that binary is the thing that is sent out. So this cartoon that I've just made of my cat wanting to communicate with me is a good way to kind of think about communication in general between two parties. Now, the problem is I have another cat, right? And here is that cute little guy. And so he basically, if he realizes that my elder cat is telling me that he's hungry, he'll come and he'll steal all the food. So what my cat wants is, he wants to send me a message that my other cat doesn't understand, right? So if you don't like this analogy, replace this and this. This is an embassy of India. This is the government of India. This is a third party that we don't want to listen to. This is your bank. This is you making some financial transaction, and that's a hacker, right? Any of these is a good analogy. So how do you defeat the hacker? How do you defeat my naughty younger cat? The way you do it is basically, you do something very clever. It's called basically the Vernam cipher, if you want to hear a phrase. And what you do is you just add a random string to it, and you send the sum of these two numbers to me, right? You just publish it on your website. And what this random string is it's called actually a private key. And if I also know this random string, so that's why I've copied this random string over here, then I can recover your message basically by simply adding the random string to the message. So let me just tell you what I've just done. I've taken an arbitrary message which translates to this number, which translates to hungry. And I've added just random strings to it. It's just binary digits, which are garbage, right? There's nothing there. Random zeros and ones. Half of them are zeros, half of them are ones. That's all you need to know. What the resulting binary number, if you convert it to number form, is basically not going to be any word in the English language. So it's just going to be nonsense. It's not going to be translated to anything. But there is a property of binary numbers, and the property of binary numbers is 0 plus 0 is 0, and 1 plus 1 is 0, right? Modulo 2 arithmetic has this property that if you add any random string to itself, you just get all zeros. all the strings are zeros. And what that basically means is that if you shared a private key, a random string of digits with me, if my cat and I shared the string, and this guy didn't know it, he cannot read what is the sum of these two numbers, which is just pure nonsense. But I can read it by simply adding the pure nonsense to my private key again, because I will simply recover the original message, right? That's the whole point of this particular encryption method, right? So now the only problem is, how do you arrange this, right? So my elder cat comes and gives me a private key, right? So this green string of random numbers. But the problem is my younger cat is listening in. So my younger cat already knows the random string, right? This is a real problem in secrets, right? If I want to share a secret with somebody else, I want my bank to know how much money I have, and I want nobody else to know. I have to encrypt the message. If I don't encrypt the message, how do I know other people can't listen to it? In fact, the problem with encryption is, how do I know that other people are not looking at the method that I'm using to encrypt it, right? In this case, this brings us to this problem of what is called certifiable randomness. I need to be able to tell you with a certificate that this is truly random. Nobody else in the universe knows this. Do you know of a truly random process in nature? It's the outcome of measurements, right? The outcome of measurements are purely random. So the trick is basically the following, which is that I take a state like this. I'll show you what this means in a second. And I actually should have put this slide first. So plus minus is basically the superposition of up and down that I showed you before. And what I've done is I've basically taken something called a tensor product. A tensor product is basically how you describe two atoms right next to each other in mathematics, right, in mathematical language. And so this tensor product simply allows for you to describe basically a state like up down. So up down is simply up tensor down. Up tensor down, I've written the mathematical form here. You take the up state, which is 1 0, correctly written here, and then you multiply it with the vector for down, which is another 2 by 1 column. So you get a 4 by 1 column, and this 4 by 1 column is the state that I've just written. So this is just algebra, and now you can verify that this state is the same as this state. These two states are the same, but they represent different measurement choices, right? This state basically is representing a measurement choice where both of us choose to measure up and down basis. This state represents a measurement choice where both of us choose to measure plus minus measurement basis. And so the way in which you defeat an eavesdropper, right, my younger cat in this example, is basically we share many of these quantum states. They're called bell pairs. And then what I do is my cat and I basically make random measurement choices. So he chooses up down, sometimes he chooses plus minus, sometimes he just tosses a coin, a biased coin, and he chooses, or an unbiased coin, it doesn't matter. I choose a biased or unbiased coin, and I choose also whether to measure like this or like this. So am I measuring along this axis or along this axis, right? And then we make many such measurements. So sometimes our bases agree, sometimes our bases don't agree. Sometimes our bases don't agree, sometimes our bases agree, right? And whenever our bases don't agree, afterwards we talk to each other and we toss out all of those. What is left? What is left is I'm measuring along down-up basis. My cat is measuring along down-up basis, and we get random outcomes. And because we get random outcomes, we have random numbers that we share, right? And that's the way in which modern encryption works, right? So this is not. So what is the bottom line? I'm almost done. I'm just about a minute away from done. What is the bottom line? The bottom line is that if you need certifiable randomness, so certifiable means that no eavesdropper, no naughty cat in the middle can actually understand what you have done, what message you're sending to each other. You use the rules of quantum mechanics. Quantum mechanics has choices of measurements, which are basis choices. Quantum mechanics has superpositions. And by choosing, and also quantum mechanics has entanglement, which I have snuck in by basically presenting you the Bell state correlations. By choosing all of these different, putting all of these different choices of quantum mechanics together, you can make a product, and that product basically allows you to in a very clear and consistent fashion, be able to eliminate any observable in the middle from being able to know what the random numbers are, and only for you and the person that you want to share the information with to know the random numbers, right? There is one little bit about checking Bell's inequalities, which I've left out just to simplify the talk, but I'm happy to talk about it. Okay, now I want to end my talk with two pieces of advertisement, which I hope that you will allow me. The first of this is that this is not a pipe dream, or this is not just purely academic discussion with no merit in industry. This is a machine you can buy right now, right? So there are many people in India who are also making machines like this. This is one of the older, well-known industries out there. It's a Swiss it's a Swiss company called ID Quantique. And ID Quantique will sell you a random number generator, which is a quantum random number generator. It's exactly the thing that I just described to you, with some additional bells and whistles, basically. And so I just want to tell you that understanding quantum mechanics and understanding the philosophical implications of quantum mechanics has a large benefit, not just to our fundamental understanding of the universe around us, but also has large benefits to the application of these quantum principles to industry and industrial activities. So what I just shared with you is a tiny example in quantum communication and cryptography, the field known as communication and cryptography. But I myself have worked on quantum computing, and this is also another field that I invite you to look at: quantum sensors. So magnetometers, accelerometers, voltmeters, so on and so forth. Things that detect fundamental measurements around us. These are enhanced by quantum mechanics, and you can make much better sensors than before. Batteries, energy storage devices. This is something that is also discussed in literature. Engines and refrigerators. So you're used to thinking of basically Carnot engines and Otto engines and Stirling cycles and so on and so forth. All of these benefit from a thorough quantum analysis, as well, as I want to just share with you. And advances in quantum chemistry as well. So if you're oriented towards chemistry and chemical and thinking about problems that are at the interface of quantum chemistry, then definitely you should think about this field of quantum computing, because it has a lot to offer. And the very last thing that I just want to share with you is, where can you go in India to do this? There are tons of different organizations. So let me actually start up north. So ICER Mohali has has a very good group. In fact, all ICERs, ICER Bhubaneswar, ICER Kolkata, ICER Pune, our friends at ICER Trivandrum, all of these folks have fairly mature groups in quantum computing. ICER Bhopal as well. And not only that, several IITs have very good groups. So IIT Hyderabad, IIT Madras, the old traditional science institutes in India, TIFR, ISC, RRI also have them. Bangalore University has a very, very good theoretical group. IIT Hyderabad has some new folks who are friends and acquaintances of mine. ISI Kolkata, the Atomic Energy Institute, Harishchandra Research Institute, and so on and so forth. National Physical Laboratories has a fountain, and they do a lot of atom experiments and so on and so forth. And last but not the least, IIT Bombay, we have a group with several faculty members. I'm one of them. And so, I hope to kind of leave this as a little advertisement for you to pursue this kind of quantum mechanics in your future, if you're so interested. Okay, thank you very much, and I'm happy to take any questions.
Okay, so anyone want to ask anything to sir? Please kindly you can ask me, or you can post your questions in the chat box.
Hello.
Hello.
Sir, I have question.
Yes, please.
Sir, I have question regarding the entanglement issue. We have seen lot of that there are very restriction, but still undeterministic properties. But there are actually thought experiments that if two entangled particles are thrown in either direction, the state of one can determine the other. So can
Yes.
you throw some light on that?
Yes, okay. So let me just clarify. Yes, so you heard a partial discussion on this clearly. So let me just clarify what the underlying controversy is, right? So this particular state that I just showed you without any kind of bells and whistles and advertisement is actually an example of entanglement. In fact, it is the prototypical example of entanglement. It's the kind of gold standard example of entanglement. It's one of the 4 Bell states. So the Einstein-Podolsky-Rosen paradox, this is the thing that you've heard, is basically relates to exactly this state. So the question that was asked was basically the following, which is that there was a discomfort with what quantum mechanics represented. And what quantum mechanics represented was basically this quote unquote action at a distance, right? It's something completely simple. Let me just explain to you what I mean by it. So suppose one of these states in front of you, right, is sent to you. One half of it is sent to you and the other half is sent to me. Remember, this is 2 electrons, right? Because when I take this tensor product and I write it like this, it actually means there are 2 atoms or 2 electrons here. So I have 2 atoms. Let's just think of them as silver atoms, and their valence electron is the electron that I'm discussing. So I have 2 atoms, physical atoms, and I send one of them to you and I have the other one. And one of them is, and what is the state of these 2 atoms? Either both of them are down or both of them are up. And in fact, there are no superposition of these 2 states, right? This is what this is saying in words, right? So either both of them are down or both of them are up. Suppose I measure mine and I see that my atom is down. What is your atom?
Up.
Just look at this state, the way I've written it, it's down and down. Either both are down and both are up. So if my state is down, your state is down. If my state is up, your state is up, right?
Yes, sir.
So what that basically means is that if I measure the first, if I measure my silver atom and I see that this is down, your silver atom will also be down. And this upset basically people who are doing quantum mechanics, because what it basically, the founders of quantum mechanics, because what it basically means is that I did something here and it influenced you very, very far away. Remember that another principle that actually Einstein is very famous for is causality, right? Is to tighten the principles of causality around the constancy of the speed of light. So what this means is that if I have 2 atoms that are so far away, right, that the speed of light, basically the light takes, let's say 8 minutes to travel between them. It happens to be the distance, average distance between the Earth, the center of the Earth and the center of the sun, the surface of the sun, I think. Then that 8-minute distance basically is something that, what that means is that if I measure down, then for 8 whole minutes, you should not know that you are down as well. But you can make the measurement 1 second afterwards, 2 seconds afterwards, 3 seconds afterwards. And what you will see is that you will also be down. So what Einstein was worried about was basically that he was basically saying, look, if I have 2 objects which are basically separated by a distance d, then nothing that happens here should be able to affect something that is happening here faster than a time d over c, right? There should be a retarded response basically on the other object, that I measured my quantum system and it collapsed into I measured and I saw the outcome to be at the ground, the spin down. This should not travel faster than the speed of light to the other guy. This is what Einstein thought. He was wrong, right? The question was so profound that in his wrongness, we've actually understood quite a lot. In his wrongness, there is a whole theory that has emerged. And the way in which he is wrong is that indeed you violate something. What you violate has to be very carefully thought about. What it did was it sharpened our understanding of causality even more. So what the modern understanding of this is basically that it's what's called information causality. So if I take, let me go back and describe the experiment again. I am sitting over here. You're sitting at the center of the sun, right? Let's just ignore all details. You're sitting at where the center of the sun is, a distance as far away as the center of the sun, and it takes 8 minutes for light to travel. Now we both share 2 silver atoms, right? My silver atom and your silver atom are correlated to each other. They're entangled with each other. And the quantum state is described like this. What this means is that if I measure down, At that very exact instant of time, you measure down as you see down as well. At any other instant of time afterwards, if you measure, you will see down. There is nothing else you will see. If I measure and see the answer is up, you will see the answer is up for at that very instant and every instant after that, of time after that. This upset Einstein because it looks like measurement results are traveling faster than the speed of light. Right? Do you understand the problem first?
Yes, sir.
Right? So it looks like something acausal is happening. Right? The moment I did it, it's happening over there. 8 minutes are not being allowed to pass. It seems like something magical is happening. The resolution of this is basically I cannot communicate any information to you. If you're sitting 8 minutes away, I cannot tell you the word hungry with this. Why can I not tell you the word hungry? Remember, the word hungry is a very specific set of numbers. I want to send 1, 0, 0, 1, 1, blah, 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 right? Let me just focus on the first 3 numbers. I want my measurement result to be up so that I get you can replace that up with a 1. We agreed beforehand that if you see up, you replace it with a 1. If you see down, you replace it with a 0, right? I want my measurement result to be up so that I get an up, you get an up. But you can never guarantee this. You can never guarantee that the outcome of measurements will be either up or down. All you know is that 50% of the time you'll get up and 50% of the time you'll get down. And this inherent non-determinism basically means of measurements basically means that causality is protected. I cannot communicate any information to you faster than the speed of light. Did that make sense?
Okay, so for given set of particles, there are 50-50 probability because they can be up or they can be down.
Yeah,
but for one, it is clear.
Exactly. So the 50-50 has to do with this coefficient 1 over square root 2. Remember that in quantum mechanics, what you have learned probably is that probability density is mod psi square, and probability for a particle to be in an interval a to b is integral from a to b dx mod psi square of x, right? So that probability for discrete vector spaces, for finite dimensional vector spaces, is just the modulus square of this coefficient, and it's 1 over square root 2, the square of which is half. So the probability in this case is half. Half the time I will see down, down, half the time I will see up, up. But you cannot tell shot to shot whether I will see up or down. And what that means is I cannot communicate any message to you, because if I'm trying to communicate adha upar, adha niche, adha upar, adha niche, you can say maybe I can tilt it all the way towards one end and I can communicate it that way, then basically you lose entanglement. So once you cross a certain threshold, you lose entanglement. So the more deterministic you want to make your measurements, if it's just the state down, down, then always basically if I send down, down, then always I know that your measurement is down, my measurement is down, but there's nothing to communicate that. I've just sent you physically down, right? Instead of sending you silver atoms, I could have just written it on a sheet of paper and sent it to you. There's no difference. So the way in which this can be used to make communication cannot travel faster than the speed of light, even though the measurement outcomes can travel faster than the speed of light. So there are kind of layered subtleties about our notion of causality basically built into quantum mechanics, actually just into non-relativistic quantum mechanics. Nothing else is required.
Thank you, sir.
My pleasure, my pleasure. Yeah. Any more questions?
Anyone else want to ask anything? Okay, so no question. Thank you, sir. So now I would like to call Sandeep sir to give vote of thanks. Sandeep sir?
Yes, hello. Yeah. Am I audible?
Yeah.
Yes, sir. Yes.
Yeah. Good afternoon, everyone. Hope I'm audible.
Yes.
Hello.
Yes, sir. Yes, sir. You are audible.
Okay. Now, it is very nice to hear such a wonderful discussion about the quantum mechanics from the expertise like you, sir. Now, when there is a quantum mechanics, when we teach the quantum mechanics, the topic, the discussions, learning is like endless. And while teaching or discussing with the student, every solution gives us a new problem to discuss. Again, While attending your talk, I also come to know that all of us also come to know after the Schrodinger cat, there is another example that give us that you have the hungry cat with you.
Yes.
And means after the Schrodinger cat, we come to know about the hungry cat and that coding and the quantum number generator. It was nice and wonderful example. So, sir, on behalf of Hindi Vidya Prachar Samiti's Junjunal College, Department of Physics, myself, Assistant Professor Sandeep Hinge, all of us, we are really grateful to have such wonderful talk, to attend such wonderful talk. We have experienced a very nice thing. And, sir, that last point that you mentioned, that quantum number generator, that was really trigger our mind. So I think one day, yes, some other day, we will have such a topic of discussion, and we will like have some special lecture from expert like you on that quantum number generator. Okay,
Sure.
sir.
Yeah, thank you very much. Yeah.
Yeah. Once again,
my pleasure.
Yeah. It's really great to attend your lecture. That was a nice talk. Thank you, sir.
Thank you. Thank you very much.
Yeah.
Thank you,
Thank
Sandeep.
you very much, sir.
Thank you
Thank you very much, sir. Thank you, Sandeep. Thank you, everyone.
Ma'am, I will just 1 second. Feedback from attendance link is shared in the chat box. So kindly please fill it, everyone.
Yeah, all of you, you are requested to fill the attendance sheet as well as the feedback form.
Okay. Thank you. Thank you, everyone.
Thank you, sir.
Thank you so
Okay,
much.
sir.
Thank you.
Participants, please fill the form.
Yes, everyone, please fill the form. Please fill the attendance form. That is attendance come feedback. Madam.
Yes.
Yeah. Shall we end the session or because the recording is still going?
Yeah. So I think question answer session is over. Can we finish the meeting? We'll end the meeting, Sandeep.
Yeah, Kiran sir is there.
Attendance
Kiran
form.
sir is there.
Attendance.
Sir has left. Sai sir has left. We request everyone to fill the feedback from attendance form. Yeah, please end the meeting. Please end.
Okay, I'm ending the meeting.